calculus, abbreviated FTC. So I will often just say FTC from now on. There's two parts of it. I've kind of seen them interchanged. So sometimes you might see part one called part two. Doesn't really matter. They both go together, really. Here's what the first part says. Let me actually read this first. Or even overview this first. It combines, I've been saying this all along, we're eventually going to combine the antiderivative and area under a curve. And this is where it happens. So instead of like we could find the area under a curve when it was a straight line or when it was a trapezoid or a triangle. But what if it's a curve? What if it's x cubed, or what if it's just square root of x? You know, it doesn't become a perfect shape that we know.
Thank you.
So what if it becomes some type of curve? We need to find the area under the curve. Well, the Riemann sums, the trapezoid rule, can only approximate. And doing so many of those is pretty tedious. So we needed a better way to find the area under the curve. And it goes back to antiderivatives. So here's what it says. If you have a continuous function f, you're on a closed interval. And remember this, we use capital F to signify the antiderivative. Or if you were at f prime, going backwards would be f, but then going backwards from here would be capital F. So capital F is an antiderivative on the closed interval AB. Then, the integral of f of x from a to b, in other words, the area under the curve, the area under the curve, is equivalent to capital F of b minus capital F of x. So what that means is find the antiderivative, that's capital F, and plug in the interval endpoints, b and a, and subtract them. And that is the area under the curve. And that will be exact. So that's an important theorem.
Isaac Newton came up with this?
Yeah, mainly Newton. But I think I put here, yeah, one of his instructors also had a similar theorem. So again, before we only knew like trapezoid, triangle, semicircle. Well, now this is powerful. Any curve, we can find the area of that curve from anywhere.
So when was this? Like 1800s?
That's a good question. I want to say probably around there.
Science book.
I don't really remember. So.
You gotta think about it, like, these guys like don't have calculators and stuff, like they're just like throwing numbers in and seeing if it'll work.
Babies.
That's insane, actually.
They're pretty smart.
Smarter than me.
One smart cookie.
Wow.
What? How? It's factual, but
Yeah, it's factual.
but me.
I'm just saying.
So let's do some examples. Calculate the following integrals. Now, if possible, I said we might check your answers geometrically. Also on here, you could check your answer with Math 9. But for these, you have to find an antiderivative. So actually doing the work here. You can check your answers other ways. So in this one, we know that it's 2. It's a straight line. It's going to be a rectangle. But let's use the rule. So here's what it says. As f2, find f of x, capital F x. So somebody will help me out?
2x.
The antiderivative. Now, something on here, no c's, because we're actually going to, it's not an indefinite integral, meaning it wasn't just that. There are numbers here, the lower and upper limit of integration, so there's no c's. All right, so 2x. Now the theorem says, well, if we do f of b minus f of a, that's going to be the area under the curve. So now I'm going to do f of b is 2 minus f of negative 3. That'll be the area under the curve. So I'm going to plug in 2 to capital F, which is this one. So I'll have 4, 2 times 2. Minus, I'll plug in negative 3 to my antiderivative, so it'll be negative 6. Also be careful there. Usually that can be, like I usually use parentheses on the second one, because it's not always just a single number. You might have to simplify something. So we get 10. You can verify that in your calculator. You can verify that with the constant rule, or you could verify it with a rectangle at 2 from negative 3 to 2 would be 5 times 2. Okay. So the next one is also going to be one we could do geometrically, but I'm going to show you the rule here on several of these. So what's the antiderivative? We're doing the area under the curve from negative 6 to 0, 2x. Antiderivative here?
X squared.
X squared. So if we do f of b, exactly, what'd you find, Sean? If we do f of b, which is 0 minus f of negative 6, that's going to be the area, thank you, under the curve. Yeah.
So that dx, that's not actually like that.
It's not affecting it, right? It's just the variable integration. So what variable are you integrating in respect to? For most, all of these, it's just going to be x. So let's plug in 0. 0 squared is 0 minus negative 6 in here. Negative 6 squared is positive 36. And so we get negative 36. Okay. I think after that, those two you could check geometrically. But from here on out, we wouldn't be able to check with the shape. So we have to rely on the rule now. So how are we doing after those? Not too bad, right?
Yeah, they seem pretty cool.
Find an antiderivative, plug in b and a. That's it. It's kind of crazy, like area under any curve or along any spot. It's just an antiderivative, plug in two numbers. Kind of crazy that that works. Okay, let's see the next one.
What's like the antiderivative do though?
It reverses the derivative.
Yeah, but like, what's it want it to find? Like the area of the derivative or of the original?
We're finding it's finding the area under this original function.
Okay.
Yeah, but to do it, we find the antiderivative of that function and then plug in values. So the next one, I'm doing power rule for x cubed. So I'm adding 1, it's 4 over 4. We could write 1/4. The antiderivative of 1 is x. So I do f of b, 4, minus f of 2. That's a. Let's see here. 4 to the 4th divided by 4. Let me just go to. I got 64. So here's where it might be good. You could do this all at once. You could also plug this into your calculator and then look at the table for 4 and 2. So if I plug in 4 to the 4th divided by 4, I got 64. And I still have to do this part, so plus 4. So really this is 68. If you don't want to, you can show that work there, it's optional. You can or you don't have to. Minus, then I plug in 2. 2 to the 4th is 16. Divided by 4 is 4. Is that right? Plus x is just 2. So 4 plus 2, it's going to be minus 6, so we get 62. I think I can do, I'm probably going to skip 6, but I think I can do 4, 5, and 7 to finish out. Okay, through the first 3? So I do 4, 5, and 7. So next to a trig one, so the antiderivative, by the way, this one's cool. Do you know sine of x is this, right?
Yeah.
So what we're doing from 0 to pi is one of those regions of pi. So, of sine x, I'm sorry, from 0 to pi, one of those regions. So this one's cool. What's the antiderivative?
Negative cosine.
Negative cosine, yeah. So we will do f of b So that's, I like to write this. You don't have to write this down by selecting f of b, which is pi, minus f of 0, that's a. So I'm plugging pi in here, so it's negative, and what's cosine of pi?
That would be 1. Negative 1.
Negative 1 right there. So now it was already negative, so I brought a negative down, and then f of pi, plugging in pi. Cosine of pi is negative 1.
Why? Oh, because you're.
There was already a negative here. Then cosine of pi is negative 1. So if you'd like, we can write it's going to be positive 1, of course. Minus, then what's f? So I got to bring, now here's where you got to be careful. The formula is minus. Then the antiderivative part here, okay, I have negative there. Now I'm plugging in 0. that does look kind of crazy there. So what's cosine of 0? 1. So again, these, let me say, this one is just from the formula. That's the minus from the formula. Then these two are because of this, because the antiderivative had a negative in it. So I brought that negative down. Cosine of negative pi was negative 1. Minus comes down. Then plugging in 0, well, I bring that negative down, and then cosine of 0 was 1. So that becomes 1. This becomes plus 1 as well. Isn't that fabulous? Well, I mean, who would have thought, come on, sine x, the area under one of those curves there is actually a whole number. It's 2. Isn't that amazing? I love that.
So fun. Super duper fun. Way too many negatives.
What is, I mean, that is just awesome how it works out.
Related.
Yeah. Pretty quick to compute too. Just do antiderivative, and you gotta plug in 2 numbers. We good with the negatives on that one? I know it wasn't. Let's finish up with 5 and 7. So secant squared. Okay, so secant.
Tangent.
Yes, I'm sorry. I was just thinking of the function itself. Secant was one of these, but this is secant squared, so it's a different function.
What's that?
So antiderivative of secant squared is tangent, yeah. So now we're going to do f of pi over 4, that's b, minus f of a, which is negative pi over 4.
So B is always on top.
Yeah. Lower limit of integration, a is on bottom. We read left to right, you know, but on these, this is really the left, that's the lower, and that's the upper. So kind of left to right, bottom to top here. Okay, so I'm plugging pi over 4 in here. By the way, you can write it like this if you want. I just don't always do that. So what's tangent of pi over 4?
1.
That's, yeah. Here's pi over 4. That's where sine and cosine are equal. And that's 1. So the sine of pi 4 over cosine, those are the same value. So the minus comes down. Okay, then f of negative pi over 4. So this is tangent of negative pi over 4. So negative values go in the opposite direction. Like negative, like this is positive pi over 4. This is negative pi over 4. So we're in quadrant 4. Now it's going to still be 1 or negative 1. Right? It's still the same key value. Is tangent positive or negative here?
Negative.
All students take calculus. Tangent is positive in quadrants 1 and 3. So it's going to be negative 1 in quadrant 4. 1 plus 1 is 2. Another shocking conclusion.
Are they all 2?
We write 2 on the test.
No, they are not all 2, but good thought. Good idea. Is there a question back there, or just making sure the hair looks good? Oh, it's fine. It's fine.
It feels weird.
That sounds looks fine, right? Do you like? I feel good.
How did that feel to get that out of your hair? Like,
All right, let's do the last one. What I'm going to do is 7. So dx over x is another way of writing 1 over x dx. Right? They just throw that dx in the numerator because, I mean, 1 is just a placeholder, really. So they can throw that dx in there, but it's really 1 over x. So this is another way to think of this one. So what is, if I'm doing the area under the curve, what's my antiderivative?
LNX.
Close. ln
Absolute.
of absolute value of x. Here's a good reason you're going to see why it's absolute value right here. Okay, because 1 over x, that function, I mean that goes, domain is all real numbers except 0, so it goes to the right and the left. So you're going to see in a second, if we're going from -4 to 2, and really what we're doing is we're getting -4 to 0, we're getting all of this. And then we're going 0 to 2, and we're getting this area. So what's going to happen, if we didn't have the absolute value there, when we plug in -4, it'd be natural log of -4, which you can't do. So that's why we have the absolute value, is so that here, when we have a -1, we can still make it work. So I'm doing f of, what was it, 2? F of b.
-2.
Oh, they're both, oh, I'm sorry. I was reading it as +2. So here's -4 and here's -2. So we're doing that region right there. Sorry. Just a little. -4 to -2. So we're doing f of -2, that's b, minus f of -4, that's a. So I plug in -2, it's ln of absolute value of -2. Minus f of -4 is ln of absolute value of -4. Let's simplify each of these. When you do absolute value of negative, turns into positive. So ln of +2 minus ln of 4. I think I left on, yeah, I left mine like that, or you could put it in your calculator and get a decimal value. I left mine like that.
How do you do like that absolute like value, like